Hello, my name is Simo Seo, and I am a senior researcher at the FKI, German Research Center for Artificial Intelligence. The title of our paper is Adversarial Deep Feature Extraction Network for User-Independent Human Activity Recognition. The presentation contents are like this. I will explain why user-independent human activity recognition is important, and I introduce the proposed network architecture with loss functions. After that, I will present the experimental results compared with the state-of-the-art methods on 4 public activity recognition datasets. So, human activity recognition using wearable sensors is an important field in ubiquitous computing. The task is to recognize which activity is being performed on the data from on-body sensors, such as smartphone, smartwatch, IMU sensors, and smart cap and smart glasses. However, it is very difficult to recognize the activities of different people because each person has a different behavioral style and the activity patterns are different from person to person. So this is a simple example video. So 4 people follow these 3 simple activities: sitting down, relaxing, and standing up. So everyone has their own behavioral style. So different sitting behavior and different style of relaxing and different style of standing up. So this video shows that every person performs differently. So this is another video. This activity is butterfly action. So it shows that it's the same activity, but different action by different human. So recently, deep learning methods have achieved state-of-the-art performance in the human activity recognition field. But creating models that can generalize to unseen subjects is still a major challenge. For example, we train neural networks for activity recognition. We train users and test the neural networks with test users, not included in the train users. So there is no overlap users between train users and test users. But if some behavioral patterns of test users are not discovered in the training dataset, then the trained neural networks may give low recognition accuracy on test user dataset. So in this paper, the goal of the user-independent activity recognition is to minimize discrepancy among domains. Here, the domain means user, and to generalize the features of different people. It is important to measure the discrepancy between different users. In the proposed method, we adopted maximum mean discrepancy, named MMD. The MMD is one of the most commonly used non-parametric methods to measure the distance of the distribution between 2 different domain datasets. The MMD regularization is normally used to align these 2 distributions among different training datasets. So we can extract generalized features by minimizing the MMD loss between the features from different users. In addition, we use adversarial learning for multimodal generalization. In the proposed method, we design a domain discriminator and feature extractor and train 2 networks by using adversarial learning scheme. the domain discriminator is trying to classify the domain labels, and the feature extractor is trying to fool the domain discriminator. It is kind of GAN scheme. So the feature extractor can extract the generalized features. But unlike normal GAN, there is no input noise vector because there is no generator like GAN to generate any data or features. Here, the role of the feature extractor is to extract a feature to fool the domain discriminator. So it is using adversarial learning scheme, but it's not same as GAN scheme. So the contribution points of this proposed method can be summarized like this. First, we propose a novel adversarial user-independent human activity recognition with 4 independent networks. The 4 independent networks are a feature extractor, a subject discriminator, a reconstructor, and an activity classifier. Second, we formulated the adversarial learning between feature extractor and subject discriminator. Third, we adopted the MMD regularization to enhance the generalization of the feature representation. Fourth, we designed the feature extractor and reconstructor based on the encoder-decoder structure to preserve the character of the original input signals and extract important information for activity recognition. Lastly, we evaluated the proposed method on 4 public real-world activity recognition dataset: Opportunity, PALM2, Health, and Mokapasi dataset. So this is the proposed network architecture. As you can see, there are 4 networks: feature extractor, decoder, this is reconstructor, and activity classifier, and domain discriminator. So the domain discriminator is trying to distinguish the person label among features from different users. The reconstructor is trying to reconstruct the extracted feature into similar to the input signal. So there is a reconstruction signal. So the feature extractor is trying to improve the performance of the reconstruction. So it means trying to minimize this reconstruction loss and the performance of the activity recognition with the activity classifier at the same time. In addition, the feature extractor is trying to fool the domain discriminator. It means maximize this domain loss, and the feature extractor is trying to minimize this MMD loss to generalize the extracted features. So this is a detailed network architectures as shown in the paper. So before training all the proposed networks, a pre-trained step is done where we train the feature extractor and reconstructor only. So this step helps improve the stability of the training afterwards by learning the content information of the original input first. As a second step, we train all 4 networks by supervised learning without adversarial learning and MMD regularization. So discriminator is trained to minimize this discriminator loss, and feature extractor here, it is not trying to fool discriminator. It is just to minimize the reconstruction loss and activity classification loss. So because the reason why we train without MMD regularization and adversarial learning is to prevent making it too easy for the subject discriminator in the adversarial learning process afterward. So we train them without adversarial learning and MMD regularization. As a final step, we train a subject invariant feature extractor by adversarial learning and MMD regularization. In this step, we freeze the reconstructor so that the feature extractor can now solely focus on classification and generalization. So now I will explain in detail with loss functions. So as I mentioned in the previous slides, in the proposed method, we formulated 4 loss functions: activity classification loss, reconstruction loss, MMD loss, and domain discriminator loss. So activity classification loss is from activity classifier. So the activity classifier training loss is defined as cross entropy loss. So here you can see the QS feature extractor. So input X is fed into feature extractor, and the feature extractor extract the features, and the features is fed into activity classifier. So after this activity classifier, we can get the losses factor, and we can calculate the cross entropy loss with ground truth label. And for the reconstruction loss, this is to reconstruct the features into the reconstruct signal similar to the input signal. So we compared the reconstruction signal with the input signal. So in here we are using the mean square error alpha loss for this. And for domain discriminator, also similar to activity classifier, we are using cross entropy loss for domain label. So here the notations are different. So the class label is Y and domain label is D. So it looks similar but different. So the number of activity class and the number of people are different. So it gives different results. So in the key, one of the contributions in this paper, here I address the MMD loss in the proposed method. The feature extractor represents the embedding features from the input signals, and we let Q of this Q of X denote E is the represent the embedding feature sets. So here S means source, T means target data set, target domains. A mapping operation phi project the features of 2 different domains onto the reproducing kernel Hilbert space RKHS and calculate the mean distance between the 2 different domains in the space. So it is MMD. So the key to calculate MMD is to find the proper phi as a mapping function to map the 2 domains to the RKHS space. Therefore, the mean difference between the 2 data distributions after the mapping is calculated as their difference. And generally, the Gaussian kernel function is used as the kernel function in the MMD, and we can rewrite the MMD loss like this with this exponential Gaussian kernel function. But in the proposed method, the task is not only measuring the distance between 2 different domains, but also measuring the distances between multi-domains. Maybe the number of domains could be 10, 12, or more than 12. So we adopt the multi-kernel MMD, and the overall MMD regularization loss can be expressed like this. And the final object loss can be expressed like this, and it can be changed to the right side. So CQP, classifier, extractor, and reconstructor should minimize the final objective loss, but the D discriminator is trained to maximize this objective function. By setting the discriminator loss with a negative sign, adversarial learning can be applied to feature extractor and discriminator. So discriminator maximizes this loss function, and extractor minimizes this loss function. And here, discriminator is only related to this discriminator loss, and other loss functions are not related to discriminator. And feature extractor is related to all of the terms of the loss functions. So in the experiments, we tested on 4 public data sets: capacity, opportunity, PAM-2, and mobile health and compared with the state-of-the-art methods, MCCNN, deep conveyor STM, transformer-like, METIR. Here, especially METIR model is to serve activity recognition and user recognition tasks jointly, and transfer knowledge across them by sharing parameters between activity recognition and user recognition networks softly, and employing mutual attention mechanism to exploit their knowledge to highlight important features for each other. So to compare with this METIR algorithm, so we can show the adversarial learning, the effectiveness of the adversarial user-independent activity recognition method. And to evaluate not only the performance of the proposed model, but also how much performance varies depending on the subject, we adopt the leave on subject out cross-validation procedure that one all data from a subject is used as a test data, while all data from other subjects are used as a training data set. So here, the Mokapasi has 14 subjects with 12 gestures, and opportunity data set has 4 subjects, but it has 2 different tasks. The first one is locomotion with 5 classes and mid-level gestures with 18 classes, and PAM-2 with 8 subjects, but one user is left-handed, so the characteristic of the signal is different as others, and mobile health has 10 subjects and 12 different activities. So the evaluation was repeated 2 times on each test set, and the results values are expressed in percentage and represented as average with standard deviation. To evaluate and compare the performance of the proposed method with others, we adopted 3 evaluation metrics: accuracy, weighted F1, and macro F1 score. Here you can see the result of opportunity, the locomotion task. So as I mentioned before, locomotion has 5 different activity classes. And here you can see proposed method gives best result, best accuracy, best weight, and best microphone score with average values. And more important thing is it reduces the standard deviation. So it means the adversarial user-independent activity recognition method reduce the difference between between domains. And Here also, this is the opportunity gesture task. So here we can see the proposed methods suggest better performance than other state-of-the-art methods. And especially for the macro F1 score, it gives better results than other methods. And here, the performance on the PAMAP2 is also better than other state-of-the-art methods. But here, the performance variance on the PAMAP2 dataset is much larger than on the opportunity dataset, because the diversity between different subjects is much bigger than opportunity dataset. And one subject, one user is left-handed, so the characteristic of the signal is different as other signals. The proposed method outperformed our state-of-the-art methods on the mobile health dataset as well. Here, even the average and standard deviation values as well. And we performed the experiments to better understand how much the hyperparameter MMD for the MMD regularization impacts the performance of the proposed model. We have conducted experiments with the hyperparameter MMD varying from 0.01 to 5.0 on the opportunity dataset for 2 different tasks and the PAMAP2 dataset. Almost in all cases, the proposed method with MMD1 outperformed that with other hyperparameters, and the proposed method with the MMD values tends to provide better performance than without MMD. But the differences of the performances by different hyperparameter values were small. Thus, the hyperparameter value does not significantly affect the performance of the proposed model if the hyperparameter values are changed in the range of the scale. So this is the conclusion. Today, we have presented a novel adversarial user-independent human activity recognition module with an encoder-decoder structure and MMD regularization. In future work, we plan to extend the proposed method to the sensor invariant feature extraction for human activity recognition and try to improve the user-independent method by adopting better feature extraction network, such as transformer or LSTM with other complex networks. So that's all I prepared in this presentation. Thank you for listening. If you have any questions or comments, I'd be glad to try and answer the questions. Thank you very much.